We are really very proud today to have our distinguished Freudenstein lectureship. So I will announce Professor Dubowsky in a moment. First, let me give you a few words about Professor Ferdinand Freudenstein, after whom this lectureship is named. And then I would like to also thank Dr. Tanaka, who has supported generously the establishment of this lectureship. So Professor Freudenstein, many of you in the audience know him personally, and to our students who are in the audience who haven't had the privilege to meet him. Professor Freudenstein is a very famous professor from our Department of Mechanical Engineering, whose world renown is based on the fact that he developed very systematic methods and advances in synthesizing mechanisms and designing mechanisms, which is a fundamental aspect of mechanical engineering. Professor Freudenstein actually was born in Germany, spent some time in Amsterdam and in London before coming to the United States at the age of 16. Yesterday I was talking to his wife Lydia, and she explained that when he applied to Columbia, there were no professors who understood the project that he wanted to work on. So very few people agreed. Only Professor Dean Baker actually offered to advise him to pursue his PhD in this topic that no other professor understood. So during his PhD, he actually advanced all these fundamental theoretical concepts about mechanism synthesis, which became so well known that today there's a Freudenstein equation that every student uses in their mechanism textbook. And he had such a huge impact on the field because he was such a pioneer. Imagine yourselves coming to a university, offering to do research in a topic that no professor really knows anything about, and then becoming the most famous person in the field, for having done such seminal work. Professor Freudenstein has been loved by so many people because he has a progeny of maybe 500, former students and students, and it's been a real privilege to have had him in, the department at Columbia. He raised the profile of the mechanical engineering department tremendously, starting in the 1950s when he was first appointed as an assistant professor. He even served as chair of the mechanical engineering department in the late 1950s. So it's really a great privilege to invite now, his former student, Professor Stephen Dubowsky, actually did his PhD degree with Professor Freudenstein. Professor Dubowsky received his PhD at Columbia, his Doctor of Engineering Science at Columbia in 1971. Professor Dubowsky also was already a family man, had worked with a small agency called the Central Intelligence Agency before that. So when he came back to Columbia to pursue his PhD, he was already an experienced, a family man. He completed his PhD degree and then moved on to great things. We were having dinner yesterday. He moved to UCLA, and then from UCLA, MIT tried to recruit him not once but twice. Eventually, they succeeded. He moved back to the East Coast. At MIT, he headed major research programs in optimal control and learning control as applied to space robotics. And he has had a very prestigious career there. And it's really, we are so glad that he's our third speaker in, this very prestigious lectureship. The first speaker was Bernie Roth, who was Professor Freudenstein's second student. Professor Freudenstein's first student passed away, so we haven't had the chance to invite him. But our second speaker was Art Erdman, who had actually studied with Sandor, who was Professor Freudenstein's first student. So Steve Dubowsky is going to be presenting today on a topic that's not related to optimal control as far as I understand. Smart solar-powered mechatronic systems to produce clean water for small remote communities. But before I invite him up on the stage, let me once again thank Professor Dr. Tanaka. Dr. Hitoshi Tanaka has actually been a great supporter of the Department of Mechanical Engineering and the Engineering School. He currently serves as the Executive Director of the Engineering Alumni Association, and he has donated money over the years for various activities related to Professor Freudenstein, and most recently this lectureship. So please join me in welcoming Professor Dubowsky, and I look forward to his presentation on this topic and a little bit of history about his time here at Columbia and with Professor Freudenstein. Professor Dubowsky.
Okay. Thank you. There it is. I'm very honored to be asked to give this lecture. The first thing I'd like to do is acknowledge that I used to call him F squared for Ferdinand Freudenstein. He was a wonderful, kind gentleman who gave his students the freedom to do what they could do, and was always very positive and supportive about all the work we did, and as a consequence, he was a wonderful advisor. And last night, I talked a little bit to Lydia's wife and some of the other faculty about how his influence permeates through my graduate students to their graduate students. And many, a week doesn't go by that I don't sprinkle a Ferdy's wisdom onto a student. So his influence goes on. He was a theoretical kinematician mostly, although had practical skills. And what I'm going to talk about, I have to admit that I was never really great at kinematics. And so he threw onto my desk one day a paper in dynamics by Dubowsky in Moscow and said, see what you can do with this. So I felt much more comfortable with dynamics than kinematics. And I do remember having, sitting in his class when I first arrived here as a master's student, which in fact is about 50 years ago. Actually, it's 50 years ago, which is a little bit strange because I'm only 35, so I can't quite figure this all out. Sitting in his class, having him talking about this 4-bar linkage synthesis and kinematics and all that stuff, and I said to myself, this guy doesn't know at all what he's talking about. And I went home, opened the textbook, and it says Freudenstein's theorem. I said, he must know something, So, but we all know our strengths and weaknesses, and so where did it lead me to? It led me over the years to mechanisms and dynamics and robotics, and you heard something about space robots. And now, as time has moved on, actually I owe it a little bit to Bernie Roth, who advised me. I said, we were talking about a book that he had, actually gave me the copy of the book, which was, what do you do when you think you've achieved everything you thought you wanted? And, and then we started to think about it, and there were some advantages to doing good. And it turns out there's no conflict about doing good and doing well. So you can do well by doing good, and that's, I think, where we're sort of moving on it. I'll talk a little bit about it, and in fact it does have a lot to do with optimal control. So the lessons are that learning from a guy like Ferdy is a very powerful thing in educating you in a way that you can solve a lot of problems, and you don't need to do kinematics to do it. And so this is work that's been going on for about 5 or 6 years now, and our lab is moved on to robotics for medical devices for Parkinson's patients, and we started to do this work on clean water through an interesting set of circumstances we'll be glad to share with you offline. But the consequences are that you begin to wonder a little bit about where the world is going in terms of what kind of legacy we're going to leave for our children and our children's children. And it becomes particularly interesting in the area of environmental issues, that you're going to have something to do to improve that and improve the quality of life for other people. And so, you know, it then boils down is somebody says, well, reveal what you're doing, and you come up with some words. And sustainability crept into this talk when I gave it sort of a similar talk about 2 months ago in Fukushima, Japan, because they're interested in the sustainability of making a country clean, and that it then leads you to where you start to say, what's the engineer's role in sustainability, in making a better life, where you use less of the world's resources, but still satisfy the needs of society. And then I added to that, while making a profit, because you realize that just altruistic behavior is a reward in itself, but it's never going to propagate unless there's money in it. That's the American way. So we've been working in clean water, and it turns out, if you believe the UN, which is, I guess, a local organization here in New York, and 1.2 billion people don't have clean water on a daily basis for their lives. So we sort of looked at that in the sense of a study which we have gets all the words in there for the students who want to study robotics and mechatronics, and optimal control was what I do, and so I had to do it. So that it's, you know, it's smart solar-powered mechatronic systems to produce clean water for small remote communities. Long title. We'll talk a little bit about that. First thing is you realize that, or maybe we realize you start doing any work in this, is that to make clean water, you need a lot of energy. It's as simple as that. It's the way God makes clean water from salt water. She shines sunlight onto the oceans, evaporates water, it goes up into the sky, condenses, and comes down as rain. That's the basic principle. So we're just trying to model, to emulate that. And the IEEE spectrum, our friends in Course 6, that's at MIT. Everything has a number at MIT. We have no names for anything. You know, every building has a number, no name. Every major has a number, no name. Every joke has a number. You've all heard that story. You don't even have to tell the joke. Just go up and say 57 and everybody laughs. See? 57. You know, acknowledge this is the head of the IEEE Spectrum magazine showing the relationship between water and energy. So to understand what we're doing, you have to understand some basic physical chemistry. You have to remember what osmosis is. So I'm going to tell you what osmosis is and reverse osmosis, and there will be, for the undergraduates, there will be a quiz following the... So the basic principle of what we're doing is PV/RO, which means photovoltaic powered reverse osmosis. We all know about photovoltaics, many of us do. That's where you essentially put a silicon semiconductor kind of material out in the sun, it generates electricity. Reverse osmosis is not quite that clear. We all remember osmosis, maybe, from high school, where water would go across a semi-penetrable membrane. You have a membrane here, and you'd have fresh water on one side and salt water on the other side, and the fresh water would go to dilute the seawater or the saline solution. And you really don't want to do that, okay? And in fact is that the water will do that until the pressure here exceeds or is equal to the osmotic pressure of the saline solution. We wanted to go the other way. And the way you make it go the other way is you put a pressure on here, okay, and that forces the fresh water back through the membrane, leaving the salt water behind. And we have a movie. So if you put the pressure here exceeding the osmotic pressure, it forces the fresh water back through the membrane. So that's called reverse osmosis, because we're making the water go the way it doesn't want to go, and we're forcing it to go through. Sort of a little bit like relationships. But I didn't want to say marriage, but you know, it's could be for those of you who aren't married. So you can think about it this way. So what we're trying to do, that's the basic principle. Okay? So the way you achieve that, okay, the way you achieve that is with a physical system, to combine it with the solar energy, is you have a solar panel right here, which has photovoltaic cells on it, okay, and the sun shines on the sun seems to have fallen down. The sun shines on the panel, produces electricity, goes through controls, has a pump, which pumps up this pressure in the saline water, the input water, brackish water or salt water, and some of it leaks through the membrane, become clean water, and some of it goes out as brine. So you can't leave it, you can't shut this off, because the salt will build up here, the osmotic pressure will go up, and it'll stop working. So you constantly have to let the water bleed out through the output here, the brine. Now we may not realize that this is high pressure brine, as high a pressure as the pump is putting out. There's a lot of energy in this brine. Okay, it's high pressure water. You can make a hose, you know, and shoot it up in the air. You don't want to throw that energy away in general. So you want to do an energy recovery on this, and we'll talk a little bit about that. So this is what it looks like. This is a rooftop system at MIT. That's our dome, and that's my office window, okay? And you can go out there, and all the equipment is in just one of these boxes. Actually, it's not a lot of equipment. The other one contains water supplies for the experiments. So that's what the system looks like. And so we're all done. We can all go home. Nothing left. And you then do an economic analysis. You go to the Sloan School of Management, and you get a guy named Steve Eppinger, and you work with him, and you say, what is economically feasible to do this kind of stuff, to provide water to people who are off the grid, so to speak. Okay? You do the study, and you come up with the idea that it's economically feasible compared to water being generated by conventional means or by diesel in these dark blue areas. That's a lot of the world. That's a lot of the world, and there's a lot of people there who need water, okay? Southwestern United States, we all know there's a huge drought going on there right now, and down in through Mexico and through Africa and Southern Africa and Australia and parts of India and stuff. Well, that's interesting. And then you say, what if? You say, what if I improve the efficiency of this system by 25%? What happens? Well, that becomes the light blue area, which is much, much larger, and it probably includes most of the people who live in the world, or a lot of them, exception of parts of China and the northeast part of the United States, like New York City, which has no problem with fresh water, and Boston. We've all had enough rain to take care of us, and Canada. And of course, this also implies you have to have enough sun to generate it, so that's not economically feasible in places that have no sun or very little sun. That includes New York and Boston, as opposed to Florida becomes economically feasible. So that's all interesting, and you say, God, okay, so maybe we can improve the efficiency of this processes. And we do control systems, and we know physics, and we know chemistry, not so well. We know physics, and we know control systems, and we know design, and we know mechanical systems, because we're mechanical engineers. And so how about if we do it better. And then you say, well, it's really where this is needed is small communities, poor communities. Okay, well that leads you to two things. Is one, it has to be practical and cost effective. That's not so bad. It has to be autonomous, meaning it can operate itself. Because you get a community of a couple hundred people somewhere in the jungle or somewhere in the southwestern part of the United States, in New Mexico, and they can put a well down and they can pump up brackish water, and they need clean water, and and you say, well, I got this computer-driven system that I want you to run and do everything. So since it's a small system, you can't have somebody standing by it tuning it all the time. And why do you need to tune it all the time? Why can't you just let it run? Well, the reason is, the biggest reason is, that's powered by the sun. And the sun is constantly changing its intensity. It's going behind a cloud, doesn't have any sunlight one day, it does have sunlight, the temperature of the water changes, the wind blows, so the system needs to be constantly adjusting. So it needs to be autonomous. You can't have a control room like this, like you do have in a giant plant. Okay, you can't. So it needs to be autonomous. The system has to be able, in real time, to be able to adapt to changing conditions. And then I said, aha, I do controls, I do robotics, so let's make a robot system that makes clean water. And so you need it to be optimal to adjust to variable solar power. They need to be highly efficient. They need to be run by local people. And then you say, well, you also need to make it so it's modular so it can be designed by non-experts. And given this idea that, we have to try to make something that's feasible for small remote communities, I had in mind, irrigation guys. If you go out to somewhere in Nebraska, hi Shane, who's watching this at the University of Nebraska, there's irrigation people. You tell them what you're growing, how much wheat, where you are, location, how much rainfall you get, et cetera, what the water is, and they'll configure a irrigation system for you. Wanted to make it so that the system non-experts could configure one of these systems for an area, so that local non-expert agents can design, sell, and maintain them. Okay, that was the aspiration. So then we looked at it in terms of the autonomy was that, so we have this system where clouds and wind and air temperature and water salinity and all the other things and water demand affect the performance of the system. And you're trying to optimize this system. So you look at it and you look at the solar panels and they have these really weird characteristics in terms of when they're efficient, how they like to play with other parts of the system. They don't play well with other parts. You have to do this negotiations of the system. The same thing with the reverse osmosis. It has its nonlinear characteristics. So you got to get everything to play together. So in trying to explain this to some of my colleagues, I try to, since I live only a few blocks from the Boston Symphony, is that the microcomputer that we would build into the system would negotiate and make all the different parts of the system play together. It's an interesting picture. I don't know if it really adds anything to it, but I sort of like it. We have a new conductor this next year, so conductor we got from you disappointed us and ran back to New York City, in case you don't know, and claimed he was too sick to wave a little stick around. Okay, so the system needs to be smart to be able to adjust its thermal characteristics, its power control to adapt to all these changes, all right? All the things that disturb it. Okay, I'm going to try to keep this. So one of the interesting things is you start to, by understanding the fundamental physics of these systems, understanding the behavior of these systems, you can find that there is in fact advantages. So, you know, this was what we learned. I learned in my PhD. You just don't try to throw a control system at it like some of our friends in the AI community. We try to understand the fundamental physics that govern the behavior of the components and then get a control system that works on it. So if you look at, for example, this is the output of voltage and power, okay, that's coming out of the PV cells. They do better when they're cool than when they're hot, okay? As the temperature increases, their power, this is the power, starts to decay for the same amount of sunlight. So hot cells are not good. The opposite with the reverse osmosis, okay? That as the input water into the process temperature increases, the amount of power that you need to get a given flow out, the amount of pressure you need goes down. And it took us, you know, a little bit of time to think this thing through. Maybe, well, the student who did it did probably spend about at least 10 minutes on it. Said, why don't we take those complementary characteristics and combine them through the thermal control so that we cool the panels using the seawater or the input water, and that'll warm the input water so that the RO will be happy, it's got warm water, and the panels will be happy, they're cool. Okay. It turns out, if you try to do that, you can do some interesting things. And this says you take the input water, you pass it through the panel, cooling the panel, okay, at the same time warming the water that goes into the membrane. And then remember this energy recovery, you don't want to throw this energy away. So that goes back and puts out the energy before the brine, from the high pressure brine. Okay. It turns out that this is not such an easy problem for people that, if you understand controls a little bit, because in fact what happens is if you warm the water too much, you degrade the membranes in the reverse osmosis. Remember those membranes? You degrade them, okay? So you don't want those to get too hot. And at the same time, if this starts to get too hot, the PV cells start to degrade. So you want to run this in an optimum way subject to these constraints. And this is what one of our PhD students did, Leah Kelly. I did mention that we find it easy, well, we find it that a lot of this work, because of doing good, seems to appeal more to women graduate students. That's not a they seem to like to do good, and the men graduate students more, this is not politically incorrect, want to do robotics, particularly robots which have guns on them that can shoot at people. So we have DARPA contracts with the advanced defense research agencies and stuff. Men run to those. The women seem to want to go to the medical fields and the medical robotics and the clean water robotics. So, she did this work, very nice work, and showed, okay, a couple of things. One is that this is a picture of our solar collector on the roof. That's the Boston skyline in the background. That you can put very inexpensive mirror panels, which are really just aluminum panels with mylar, luminized mylar glued to them, and focus more sunlight onto the PV panels. Okay, and then you're running water back through heat exchangers on the back of these panels that cool it, that let you increase the amount of power put out by the panel very substantially. And then you wind up with this thing. So you have this cool water coming in, which I've already explained, the warm water going on there, and you got the smart control electronics controlling everything. Okay, and you have to put in a bunch of valves, and you have to do a bunch of control algorithms based on these valves. You also have to write a lot of equations in order to be able to do this, and this is one of the things that we do, and that's, Ferdinand told us we should not be afraid of equations and mathematics and stuff. So we write a lot of equations, and they're partial differential equations, and you set up the control system based on that. But I don't want to get too much into that. You set up the controller, which is a multivariable input and output controller, and you can show here through simulation that as sun rises, this is the temperature of the various components in the system, that as the sun rises and things start to get too hot, you turn on the thermal controller and it cools down the panel. This is the temperature of the panel, and it also improves warms the water. But the payoff is in the amount of water produced. Oh, more equations. So we went to Cyprus, well, at least we went to Cyprus and played on the beach and talked to the Cyprus Institute, and we said, we'll do a heat study for you in Cyprus on this and see what we can gain for you because everybody know that Cyprus is in the middle of the Mediterranean somewhere? They get fresh water from their cisterns and places like that about 3 days a week during the summer. And the other 4 days a week, they have no water. Baths are very expensive in Cyprus. So we went there and we did this thing. And lo and behold, it's interesting that Leah's thermal control system improves the water efficiency, the amount of water by about 50%. If you remember, maybe it's another slide, the punchline later. Okay, so 50%, of course, we don't ever believe what we believe from our analysis because simulations the more you do it, the more you think it's the real thing. So you have to go to the laboratory and do it. So we have our experimental system, which is fully instrumented, and this is all the details of the power controls and the system on that. And that's what it looks like, and that's what our system looks like on the roof. We show that a couple of times, okay? And what happens is you then can run the system. Let me show you a video. This is a video, look at that, of our system on the roof. And you notice this was my office back there. They put it in a big plastic bag. Something about the parking lot down below it is where the president of MIT parks his car. And this parapet here was beginning to fall down and might hit the president of MIT and his car, her car. So they put my office in a plastic bag for 4 months. I said, what's the big problem if the bricks fall on the president of MIT? You know, she doesn't teach any classes. You know, she doesn't empty my waste paper basket. Who needs it? It didn't go over well. So I got my plastic bag and I sat in the dark in there. Okay, so this shows you these experimental results here. And what you're going to see here is the amount of sunshine that happens, falls on the panels. We're measuring that. This is a time-lapse photograph. This goes across a whole day, and this is the amount of water produced. And you see that the smart controller can adapt to the changing amounts of inputs, solar radiation. Okay, and if I can figure out how to play this. And the other thing is, we don't normally, so they put a fish tank here and dyed the water blue so you can see the clean water coming out. The salt water is in this box, okay? And we had to empty it several times over the day. And how do I do that? Okay. And if we had sound, what you'd hear is, oh, there it goes. So this is the insulation. And because it's nonlinear, even though as the sunlight is building up and the power is building up, you actually are not producing any water to speak of. Panel is tracking the sun. You can see the clouds going over it. You can see a couple of students there running in and out over the course of the day to do various things. It is operating autonomously, but they're checking to make sure. I don't even know what they're doing, pretending they're working. So the sun goes out there. Here is dips down as it becomes very cloudy, but the system keeps producing water, and as you can see, the water here is building up. It gets emptied, and you can see a little rubber ducky there floating around in the tank, and his name is Senor Ducky, and I have no idea why he's in there. And the sound to this movie, if I were playing the sound, is "Rubber Ducky, I'm awfully fond of you." When you start to have women working on your research projects, you get results that are a little bit different than what you'd expect. And so we'll play that again, give you a chance to see what's really happening. So we're producing clean water. And it seems to be working just fine. And it's working well so let me move on to the next slide. You've seen that. So what's interesting, what experimentally and the simulation results match pretty well. This is without thermal control. This is with thermal control, okay? And that's a 57% improvement in performance of the system. That's dollars and water on the output. That's not a theoretical efficiency improvement. That's the amount of water we're producing. And remember this chart. So this shows the result, 57% experimentally. Remember this chart with 25% improvement? We're able to get a 57% improvement by using our control system knowledge and being able to configure it and using the embedded smart computers. So that went on, and then we started to do power consumption. I'm going to move this along. We're not going to go power control, but there's a lot of equations there, and again, they will be on the midterm exam. And we won't talk too much about that. One of the things is to do optimum power, you want to have a computer-controlled energy recovery device. Remember the part with the brine, the high-pressure brine? You need to adapt that. And that was another project done by Elizabeth Reed, in which she designed a sort of cool computer-controlled nozzle. And in spite of the fact that when I was at Columbia, we talked about this, fluid mechanics, again, was not my strong point. But I found that when the very bright students come in, I think I learned this from Ferdinand, but I don't think he actually ever said it to me. He didn't want to tell me the truth. Is the secret of dealing with students who are working on research is to bite the inside of your cheek when they're telling you what they're doing. Two things. One is if you bite the inside of your cheek, you can't speak and say anything stupid that'll get in their way. The other one, if the pain in your cheek is enough to keep you awake while they're talking, they think you're interested in what they're doing and they keep working. So that's a secret that, I don't know if he ever bit the inside of his cheek, but he'd always sit there, listen quietly while you were doing what you were doing. So I didn't like fluid mechanics. Anyway, so she did all this work where, these are great video, where she's got these computer-controlled nozzles that are maximizing the profit of the energy recovery as a function of the system characteristics. And then she's built this wheel, and we call this design, and oh.
Okay, now it is.
So it's cool. How many people are doing turbine work these days? Not a lot. We wind up having to really go back and look at things that mechanical engineers used to do a while ago. And you can hear the women. Can you hear the women talking in the background? They like to chat when they're making videos. But they're chatting about technology, which is different. I was walking down the hall. MIT has this hall called Infinite Corridor. that's very long. It's not quite infinite, if you've been there. I was walking behind two co-eds, and one said to the other one, you know what I'd really like if I really would like, and I figured she'd say something like, you know, I don't know what she'd say, high heel shoes that wouldn't break or anything. She turned to the other woman and said, I'd really like a 16-bit D to A converter with really low noise. So we're very happy with our students, which are now, by the way, in mechanical engineering is about 48% women. So times are changing, and with great enthusiasm on my part. This is Amy Bilton's work. So we have Elizabeth, and we have Amy, and we have Leah. This is how to design systems that, remember, the experts, given a set of requirements, a physical location in the world, the demand, the nature of the sunlight that you might get in a given location, fouling factors and reliability and issues. How do you design a system to meet the needs and to do it all automatically in the system so that you then can order it from available industrial components, which we call an inventory, and it's shipped to site and some guy hooks it all up and turns it on. Okay, and so it turns out that even for this small number of modular components, the number of ways you could hook up these modular components is 10 to the 107th, which exceeds the number of atoms in the universe. So even a very fast computer could not sort through all of those in any meaningful way in anybody's lifetime. So the challenge there was to reduce the design space. And what she did in her work is set up a set of filters and tests that were very, very simple, easily computed, that rapidly truncated or pruned the potential design space. And they were all based on understanding of the physics. Now, some of the understanding was pretty simple, like you don't hook the output, the electrical output of a solar panel into a water hose. But then there are others like that. It gets more, they become more and more elegant, and this approach was done by Shane Faraday in his PhD thesis on robotics. So it was applied. She applied it here with a number of extensions that also included the uncertainty in the environmental factors, meaning the sunlight and other things, which was really cool. And then she set up a graph topological tree or a structure that showed the way things were hooked up, and using graph theory. And then, and I should point out that Ferdinand had, you know, this all looks cool and new, Ferdinand had a PhD student in the mid-70s who was using graph theory to configure mechanisms this way. So, and then she used genetic algorithms in the final form to determine the final configuration. Nice thing about genetic algorithms is, for those people that are interested in such things, is that they're very nice for looking at system configurations, because they're really dealing with ones and zeros, or chromosomes, literally chromosomes, and which can be represented. So anyway, that's what happened. So that's the state of the work. We'll try to finish up relatively quickly. So then what happens is you show that it's theoretically feasible from a financial, from an economics point of view. You show maybe that the it's more feasible, or you can show that technically it's feasible, and you can support it by experimental things. But then Senor Ducky comes by and he says, how many people speak Spanish here? What does it say? Exactly. So you've got to get out of the laboratory. Too much of the work we do is, and we always listen to Senor Ducky, it's too much of the work we do in the academic world is academic. We take it and we write a paper, and we publish it in a journal, and then we move on to the next problem. So now that I've moved on and I'm almost 36, I say, you know, we should try to take it out to the real world and see if we can really use it and help people. What's interesting is, I'll tell you a little bit aside, you never know how this is going to happen and how it's going to go. But I wind up giving a seminar in Michigan, right, on clean water. And they have more clean water than New York has. And so, but you know, it's near my daughter. So I said, sure, I'll go give a seminar on this stuff. And a guy came in from Battle Creek, Michigan. Everybody remember Battle Creek? Anybody remember what's in Battle Creek, Michigan? Kellogg's. They sell cornflakes. A lot of cornflakes. They have a lot of money. And the Kellogg family is very, very kind, very, very good. So they said, why don't you take this they came over and they said, why don't you take this technology down to someplace we're interested in, Mexico. Because there's a lot of small villages in Mexico, they don't have clean water. So 2 lessons. One is, you never know where the opportunity is going to come from, one. The second one is eat your cornflakes to keep this project going. Okay, so we went and we focused on the Mayan Indian. It is politically correct to say Mayan Indians. We asked the Mayans. They said, PC, what does that mean? You know, but there are these small Mayan villages down in the middle of nowhere on the Yucatan Peninsula, okay, surrounded by these wonderful Mayan ruins and living in little simple places. And we went down there, and we have been going down to that, to try to make clean water. The water situation is they have these surface ponds, okay, where they catch rainwater that are there during the rainy months, have some water in them, and they drink that, okay? The only problem is, so do the pigs, and so there are 2 pigs there in a surface pond that they're drinking. They don't want to drink that. They have deep well water, which is highly brackish, which is no good for anything but washing your car if they had cars, but they don't have cars. So there's not much they can do with it, and they deliver it to the houses by squirting it into these systems. Or they can buy clean water from the Coca-Cola company in 20-liter bottles. That's a local facility there. The only problem is they don't have any money or enough money to buy it. So they don't do it. So what they do is they drink this, they're supposed to boil it, and they won't drink that, and they wind up with these parasites and all kinds of problems. And they also don't have any aspirations about, it's subsistence farming area where they burn parcels of the jungle down. They cut it down, burn it, plant corn and other things, and that's it. So we went down there, okay, to a village called La Macolona, and which has about 900 families, okay? And we designed a system to be put down there. It was assembled by, we worked very closely with a local NGO, Foundation for the Peace, okay? We designed it, okay? And it all fits in this little house, this little garden shed that we brought with us from Cancun that we bought at Home Depot. And Amy Bilton, who's now a professor starting in September at University of Toronto, this is known as her house. You know, it's her first house. The system is in there, and this is what the overall system looks like. with the water coming into a tank, sitting on a bunch of concrete blocks. And we ran this, okay? And it works very well, okay? Reduces the total dissolved solids, which is the problem in the brackish groundwater because it's sitting on a seabed. Anybody know anything about geology knows that the Yucatan Peninsula is just a big seabed that's been lifted up by the big asteroid that landed in the Gulf of Mexico and will, and that's why it looks the way it is. By a factor of 10, the things like the alkalinity and the hardness have been reduced down to ideal levels in the system. One of the interesting things is we owe to the Chinese has reduced the cost of power, PV, panels, from when we started this project at $5 a watt, the basic cost of buying a panel, to about 70 or 80 cents a watt, is that we can sterilize pathogens and contamination using very conventional ultraviolet lights powered by the PV. And it doesn't cost anything, basically. So we did that, and we looked at our competition, which was this bottled water from the Coca-Cola company, which they're selling for 20 pesos for 20 liters of bottle. They can't afford that. The people in these remote villages can't afford that at all. Not only that, it has to be driven in about 60 kilometers each way over dirt roads. And the village of about 500 people, 90 families, has 3 trucks, of which 1 or 2 work at any given time. And they don't send their kids to high school because it's too far away. It's in this same place that you can get the clean water. So if they did have trucks, that's the next thing, is that somebody should give them a way to get the kids going to high school. The cost here, including the system operator, okay, and the water and the chemicals to refurbish the system and the materials, is less than 1 peso, which is a 40 reduction in cost. If we sell the water, if the village sheriff who runs the village, elected individual, were to sell the water for 24 pesos, it means the system would pay for itself in 1 year. Our fantasy is that these systems will do this, okay, and actually this number's dropped down to 2 pesos now, that each system will begat, that's a biblical word, I guess, another system every year going to another village. And you can look at this geometric progression that you could cover a whole area. The only problem is we don't know how to implement that. We've been dealing with the Sloan School of Management and all of that, but haven't yet come to a solution for it. So the conclusion is that lack of clean water is important for many people. Engineers have a responsibility to do something, maybe not. Depends on your view. Some engineers just want to make money. The solution to these problems will require an interdisciplinary research team for all kinds of things. They will need to work in the field. Now that's an important thing. Even in our medical areas, what we found is the big mistake is to try to do experiments on graduate students. It doesn't work. Unless you go to the people that are going to use it, it still doesn't work. So the water is producing clean water now. It can be profitable. It can be profitable. I think that Ferdinand would have approved of this work. And I think his guidance and leadership here at Columbia was important for all the students in making them move on to do really exciting new things. And, you know, I think to some degree in the introduction it was saying Ferdinand came here and did his work without working in a new field working probably with encouragement from Baker, but going out and doing something they never did before, and they didn't know how to do, and he wasn't afraid of making a mistake. And I will admit to you, when we started this project, I had no idea about this technology, none. But I think, you know, he encouraged people as students to do things they didn't know how to do. And that's important for all of us to do with our students. I want to thank the people that worked on the project over the last 5 or 6 years, including Senior Ducky, and the sponsorship from MIT and Kellogg and the KFU BPM. The one lesson for those academics might be hanging around is that even doing good work can result in important intellectual results and a lot of publications. That you don't have to, because you're trying to do this kind of work, that you don't need to do publications anymore. But I thank you for your attention. I'd be glad to answer any questions.
Questions from the audience? Thank you, Professor Dubowsky, for this excellent question. So I'm going to get started with the questions, so I encourage everyone else to participate. So these osmosis membranes and the device that's installed in this village in the Yucatan, how often do they need to be replaced?
The membranes need to be replaced every 3 to 5 years.
Okay, they last that long?
They do last that long. They have to. The system will generally use an automatic back flushing to clean the membrane about once a week. And you can also use a chemical cleaning to clean them. But it turns out that if you're using commercially available components, we all know that, I don't know if anybody knows this, that if you look at large production items like dishwashers, they sell for about $4 a pound. Which was a lot more than what dinner cost last night. So the idea is that RO technology, the small-scale RO technology, is commercially available, and the individual components are commercially available at a reasonable price. We have, I hate to say it, but we have the Koch brothers to some degree to thank for that.
How many of the components were printed in your design? I noticed the turbo was probably printed, 3D printed.
The turbo was, yeah, but we don't, that was an experimental system that was in fact printed for us in Saudi Arabia. I'll explain later why that was done there by Aramco. You take what you can get, but nothing otherwise. But that's not part of the system. It turns out for the Mexico system, there's enough sunlight in Mexico, okay, that we don't need to do energy recovery in order to make the system technically feasible. We just blow off the brine and don't need the energy recovery turbine. Variable energy recovery turbines, variable energy recovery devices are available for much larger systems. That remains sort of an interesting question if you really, how do you, the very small scale energy recovery. It turned out when Amy ran her models on different places in the world, places like Mexico and Cyprus didn't need energy recovery to be economically optimal.
Yes.
How do you dispose of the brine?
That's an interesting question, and in fact, it's a very good question, and we get a lot of answers about that. If you have a seafront facility, which this is not, okay, this example, you dispose, for these small systems, just put the brine back into the ocean. It's very happy there. and you don't put out enough to have a brine plume that will affect anything, because they're small scale. This is what we're doing, and there are villages like that. Here in the Yucatan, basically all the soil is seafloor, and seashells essentially is calcium carbonate and the water is coming out of that, and that's why it's so brackish, full of dissolved solids. And we're just putting it back into the ground. And it has no effect at all, because in fact I should say no effect at all. We know of no effect. It's fine. That's what Coca-Cola does. The feeling is that we actually use French drains to get it back in the ground and stuff. But when you get below about 3-4 inches of topsoil, it's like the White Cliffs of Dover. So there's no problem about spoiling the groundwater in that sense. But that's a good question. That's an ongoing question about what you do. And we did calculations where we could do evaporation, surface evaporation, because it's warm down there. And you'd wind up with, every 4 or 5 months, you'd wind up with a 55-gallon can of soil, essentially. So if we wanted to do that, you could dispose of it that way. That's a good question. It's very much of a local issue where it is.
Sunil, so approximately how many gallons of water were you able to get every day, and how does that compare with the needs of the village in Yucatan that you want to pay?
Good question, exactly. 1,000 liters a day, okay? Which more than needs, the need versus what they'd like. For drinking purposes, we figure about 40 to 60 liters per family per week. So if you do the computation, you find out the system is more than adequate to meet the needs. But the system is in liters per day, which is about 250 gallons per day of fresh, clean drinking water for 100 people. Okay, so that's about, what, 2.5 gallons per person per day? Yeah.
Would you comment on the relationship of your work to what they do in Israel about
Yeah, sure. Israel is a totally different place. It's not a third world country. It's a modern economical thing. We have projects in Israel in the medical area. They do desalination using, in places like Ashkelon, which are the biggest desalination plants in the world, and they are desalinating water using conventional energy, and they could afford it. What's interesting is that they can do so much desalination is that they have to muck up the water a little bit because it's too pure, because drinking distilled water is not good. But they're using different, in a lot of places, and in part this work was funded by Saudi Arabia, the earliest work, and I can say that I think I'm the only one in the world who was funded at the same time by Mafat, which is the Israeli Defense Projects Agency, and the Saudis at the same time, in the same lab. And keeping them a little bit apart was interesting. So Israel is a modern country like Saudi Arabia, which can well afford energy. In Ben Gurion, they are looking at solar-powered desalination, but working with a totally different set of constraints and environments. The whole problem in terms of scaling changes when you start to go large scale. You start to get into large thermal plants where you have thermal processes, flash evaporation, and you have operators, people sitting there, who are able to, you have teams of designers who will design and build the plant and then operate it, that control room and things. So that's the distinction between Israel and what we're doing here. I hope that answers your question.
Thank you.
Yeah, I was wondering what was the setup cost of the Mexican unit in getting Amy's house going? What was the cost?
Well, you know, I think the setup cost is, because you have to pay the graduate students anyway, right? And it's built from commercial components. So I think the real question is, what do we assume in the cost of recovery, okay, time for recovery, what the cost would be if we didn't send Amy, Steve Dubowsky, Heather, you know, and Leah, and down to do it, and didn't have the NRO, the NGO working down there. And, you know, it depends on so many factors, meaning the amount of sunlight a given environment gives, okay, and what the water demands are and all that. The answer is a few $1,000s would be the cost of the components, and if it was done by a technician or local technicians who would go down there, be local people to do that, and were trained to do it, and you had a company. You know, the numbers are very funny because, in fact, is that the operators, we're going to be paying the operators part of that recovery, you know, and we figure 10 pesos an hour is a great wage, really great wage, and that works out to be about 80 cents an hour. We're not paying, you know, West German rates for labor, okay? One of the interesting side effects is that the people in these villages are, as I said, subsistence farmers and only have elementary school education. They're trying to bring better education to this area. But we're hoping that the guys who run the system at 10 pesos an hour, which means they're going to work about 4 days a week, 4 hours a day, to distribute the water and then put them in the 20-liter bottles and all that, will become the highest paid people in the area. And running this high technology system will be role models for the children in the village to say, you don't have to be a farmer with a machete, that there are other opportunities. And you should try to go to school, you know, to high school, because you could move ahead. So a big part of our selling point and the bigger picture with Kellogg is that this is all a bigger picture of making the people self-sustaining economically, letting them grow, let the people that assemble and build these systems down there, let them be local individuals. The same kind of guys who repair the taxi cabs could build these systems. So it's all part of a plan to change the nature of their economic culture and their sense of their view of potential, what view of life is like. So, you know, this by itself is a piece in a much bigger puzzle to enable the quality of life of the indigenous people living in these areas to have a much better life. So that was a long answer to a short question. I hope I answered your question.
Professor Dubowsky, thank you so much. Let's please thank Professor Dubowsky.
Well, thank you.